Is it getting recorded?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. Let us start today's. So last some week we started the introduction and all. So let us run through what it is in the first unit, right? We already started the first unit. Let us go for a again recap of what we studied in the last class. So in this class or in this unit, you will be studying about the rate equations for heterogeneous reactions, how to write the rate equations for heterogeneous reaction. Then adsorption isotherms, different isotherms are there. Then how to write the equations for a rate of adsorption, desorption and all. If there is a surface reaction happening and how to write the rate equation for a surface reaction control. Then when there is a heterogeneous reactions in place, how to write down the rate controlling steps or what is this rate controlling steps. So last class itself we discussed reactions gives products in presence of a catalyst. This catalyst, the reactions can happen in a heterogeneous reactions. There are two types. One is catalytic and non-catalytic. Catalytic in the sense reactants produce products in presence of the catalyst, or reactants produce catalyst in the absence of catalyst. Both forms heterogeneous. Heterogeneous in the sense either the reactants or the products, at least more than one phase should be there. If all the things are in the same phase, then we call it as homogeneous. So we discussed about the examples of catalytic type heterogeneous reactions. Here it is gas solid, gas liquid solid reactions. Again, the catalyst will be there. So some examples we are giving in the last class. This for non-catalytic heterogeneous reactions. That is, there is no catalyst, but the reactions are heterogeneous. That means at least one phase is different, right? So minimum two phases are present. So if there is a gas liquid or a gas solid reaction, this is the example. Like that gas liquid reactions are also there. They especially adsorption will play a very important role here. Other than that, there can be a liquid-liquid reactions where there is a catalyst, a solid catalyst. Last class also one boy asked, when there is a liquid-liquid reactions, how it can be a heterogeneous. Heterogeneous because liquid-liquid reactions are there. It is happening in presence of a catalyst, or there may be a solid, some the what do you call, the product which is coming out may be a solid, right? So at least one more than one phase is there, right? Either it is a catalytic type or non-catalytic type. Here the examples we are seeing is non-catalytic. There can be a liquid solid reactions. Some examples we saw in the last class. So how to write the rate expressions, right? This is the biggest topic. Generally, we assume that rate equations, if there is a heterogeneous reactions, there are number of steps which will happen inside. The number of steps can be a series or a parallel. If there is a parallel reaction, then the overall reaction or the overall rate, you can write as sum of the individual reactions. Sum of the individual reactions. Second, let me, yeah. This is sum of think this pen, I just want to make as red ink, but somehow it is not coming here. Generally, it should come here. Okay, let us do same. So if there is a parallel steps, then what we do is the overall reaction is a sum of the parallel steps. That is sum of the individual steps, which will give you the overall reaction rate in if there is a parallel. Generally, what we assume in a heterogeneous system is a series of steps. So when there is a series of steps, then you will write overall as the rate of first reaction is equal to the rate at the second reaction is equal to the rate at the third reaction is equal to rate at the nth reaction. So this is at a steady state condition. You know what is steady state condition, right? So even there is no changes with respect to the time. So what we assume is the reaction of 1 or the rate at 1 is equal to the rate at 2 or that is equal to the rate at n. So this is what is more important in heterogeneous. So what is the steps? I'll with the time we'll discuss more about what are these steps, different steps which is in series, right? So this we already discussed. You can write the rate based on the volume of the reacting fluid or mass of the solid or interfacial area or interfacial surface or mass of a whatever you want. So generally we use this expression. Generally we use this expression more often in homogeneous reaction. Homogeneous reactions we will use more of this expression, that is V. V is the volume of the reacting fluid. It is not the volume of the reactor. It is the volume of the reacting fluid. But generally in heterogeneous things, heterogeneous reactions, we generally go for the rate as minus 1 by W. W is nothing but a matter of the solid use. Rest of the thing is same. dNA by dt is nothing but moles of air reacted with the time. So 1 by W is the mass of the solid, or 1 by S also you can put. That is nothing but the interfacial surface area. When you are using this, then what will happen is volume is having a unit of meter cube. W is having a unit of mass of a solid, that is kg. This S interfacial surface area will have a unit of meter square. But dNA by dt, dNA by dt, dNA by dt will have the same unit. So based on this particular thing, your unit for this left hand side minus RA or minus RA dash or minus RA double dash will change. So they can give a 2 marks question. Knowing this rate, what will be the unit, that is the unit of this rate, you can find out what is the unit of this rate, because you know the unit of this rate is nothing but moles per meter cube per time, and you know this is moles per time, W is kgs, then you can find out what is the unit of this. So you can rearrange, because moles of A per time is nothing but dNA by dt. If you want, if you equate all this is nothing but minus RA into V, that is equal to, because the dNA by dt is same, that is equal to minus RA dash divided by W into W, that is equal to minus RA double dash into S. So knowing one rate, the unit of one rate, you can calculate the unit of another rate, knowing your V and W, right? So that is what he is giving here. This already we discussed in the CRE1, this, right? So in heterogeneous, we generally encounter these kind of rates rather than this kind of rate. That does not mean that we won't use this. We will use this also, but along with this, we'll use this also, right? So let us go to an important topic of rate controlling step or rate limiting step. Generally, rate controlling step, or otherwise called as rate limiting step. So the name itself suggests rate controlling. That means that the resistance offered in that particular process is more. Even the resistance offered in that process is more. That means that the time spent by the reactant molecule to cross that particular step will be more. Once you cross that, immediately you will have the next what do you call step or something like that. It is just like going from here to Sholingalur or Tiruvanmayur. You are assuming that there is only one big junction at Sholingalur. The moment you cross Sholingalur, you assume that later there is not much of above the Sholingalur till Tiruvanmayur. There is no not much of traffic. So your time will be very less, but the time spent for you to cross the Sholingalur signal may be more, right? So that is what we call a rate controlling step. Rate controlling step or rate limiting step is the step where the resistance is more. When there is more resistance, the reactants will spend more amount of time in that particular step, right? Let us assume there is a reaction. A gas plus B solid gives you R gas, right? So what does that mean now? This is a heterogeneous reaction. This is a heterogeneous reaction. Two reactants are there, one product is there. The reactants are gas and a solid, which is getting reacted to give you a gas as a product. So let us assume there are some conditions. Let us assume first order with respect to gaseous reactant. This reaction is a first order with respect to gaseous reactant. So when there is a gaseous reactant, this is a first order. So when you are writing the rate, you can write as minus RA is nothing but K if there is some rate constant into CA, because it is first order. So let us assume B is a solid. Earlier itself I told you B is a solid. B is a solid. So you can have the solid can change size with respect to the time, or solid may not change size with respect to the time. So let us assume there is no ash formed on the solid surface. Solid is getting reacted with gas and forming a gas as a product. So with the time, there is no ash which is being formed. There is no ash which is being formed. That is in the sense the solid is just like that, right? So what is happening? How this gas is reacting on the solid? Yeah, can any idea how it is going to be present? Now let us assume this is the solid particle. Let us assume the solid particle is spherical. The solid particle is spherical. Then there is one more, that is this solid particle here. The gas is there, right? This is, let it be the gas phase. And this is the solid particle. This is the solid particle. Now what is happening? Now a gas, which is a molecule of a gas, which is here. Let us assume there is a molecule here. That should penetrate through this particular gas phase and go onto the surface of the solid. Am I right? So a gas, an individual gas, there is a bulk gas here, right? This is a bulk gas. So the gas molecule should penetrate, or we call it as diffuse, into the gas, then reach the solid surface. That is the step number one. Once it reaches the surface, then what will happen? It will sit on the surface and then react on the surface. So second step is reaction. First step is diffusion. Second step is reaction. There can be a third step where once it gets reacted, the product is formed on the solid surface. That product should desorb from that particular solid, again come through this particular thing and then go to the gas phase, because The product is a gas. Therefore, the third step is again the product. Yeah, you can see transported from the solid surface, right? Yeah, you can see here. Gas A is transported from the bulk of the gas to the solid surface. So there is a solid which is almost entire solid is gas is being present around the solid. Therefore, the gas molecule should penetrate through the bulk of the gas and reach the solid surface. This is the step number 1. That is solid surface is B. The second step, once it reaches the surface, then what will happen? The reaction will happen. A surface reaction between A and B. A is the gas, B is the solid. There, the reaction is happening on the solid surface. The third step is, once the reaction is happening, the product is formed. That is, the gas is formed. So here there will be some unreacted A, there will be some product R, and there will be some unreacted B also. But the gas which is being formed, it should transport from the solid surface to the bulk gas. Again, it comes out. Am I right? The product which is being formed, it leaves the solid and comes out and joins the gas phase. So these are the three steps by which the reaction is happening here. Out of these 3 steps, only one step is a rate controlling. That is, more number of time the reactant or the solid particles or the product is spending more amount of time in a particular step. We have to find out what is that step out of these 3. Yeah, I stop here. Any doubt, ma? I don't know whether I'm making my point clear or not. Yeah. Yeah. Some feedback can you give, one of you? Anyone, ma? Any feedback you want to give?
Sir, could you repeat that last point? What are we trying to find?
Yeah. Now you see here, this is, let you assume there is a coal burning. Yeah, those people who didn't understand this, I'm explaining with one diagram now. I drawed the diagram, but I didn't give the example. Now let us assume this is a gas and this is a solid, right? So we'll take one example. So let A is a gas, that is oxygen. B is a solid, that is coal. Will give you the product CO2, correct? So now I'll give you one example here. This is the solid. This is the solid, that is coal or carbon. Oxygen is being present somewhere. So this particular will be, oxygen will be surrounding this particular thing. So oxygen molecule should go to this particular surface. That means that it has to pass through this bulk. Yeah, there will be one resistance here. So oxygen molecule should pass through this bulk and then go to the solid surface. Here. Then the reaction will happen at the solid surface. That is the second step. Once there is a reaction formed, CO2 is formed, right? It is also gas. So CO2 leaves this particular, from this particular place. Again, it comes back. Oh, what is that? Again, there will be some resistance because there is a surrounding gas, that is oxygen. So it has to penetrate through this particular thing and then come out, right? So this is one step, that is oxygen penetrating through this particular bulk layer is one step. The second step is, once the oxygen reaches the solid surface, there will be a reaction on the surface. That is the second step. The product from the surface, it will be desorbed or whatever you name to the, again, the product. That is, it should desorb and diffuse through this particular gas film to come out. That is the third step. That is the product, and this is the reactant. So reactant is going in, reacted, and then product is formed. Now, any doubt? So you can see here, this is the air. In the air, lot of in the air contains of a lot of what do you call? Lot of compounds. Nitrogen is also there. Oxygen is there. Argon is there. In that, oxygen penetrate through this particular layer. That is the gas layer. Yeah, you can see here. This is the gas layer and reaches the solid. Then reaction will happen. Then the CO2 which is formed, it will be again transported through this particular bulk and then comes out. So there will be one resistance here going through this particular what do you call bulk phase, bulk gas. Then there will be one more resistance here near the reaction. Then the third resistance will be coming out through again the bulk. So that is the gas film. The resistance offered in this particular film is called as a gas film resistance. This is the solid. Yeah. Any doubt here now? Yeah, I stop here. Yeah. Some of you can give some feedback now.
Got it, sir. Understood.
Right. There will be 3 steps now. So you cannot write your rate as if there is a first order with respect to this particular thing. Then how you write generally is this is A plus B gives some product R. Now if you're writing with respect to this minus RA is equal to K into CA. That is how you write, right? CB and to CB you write, right? Because if this is first order and this is first order, you write your rate as minus RA is K into CA into CB, correct? But here you cannot write like that because this K, what K you write? There will be a resistance here, there will be a resistance here, and there will be a resistance here. So you have to write this K as a combination of the resistances, just like individual mass transfer and overall mass transfer. You know the difference between these two? Individual mass transfer and overall mass transfer. This is like a overall. This comes when there is a homogeneous reaction. There is no individual there. But here there are different phases involved. There is a gas phase, there is a solid phase, again there is a gas phase. So you have to write your rate in terms of these resistances. These are the individual resistances. And if you want to get an overall resistance K, you have to make that individual resistance into sum of this. You know how to write this overall resistance in terms of individual resistances. That is what we are going to do now. Let us go to the next slide. I think some of you will have a lot of questions. Please hold for some time. Now we will do a derivation. For a homogeneous reaction, you can write K like this. But for a heterogeneous reaction, when there is a change of phases, you cannot write this K like this. Again, by the way, I am talking only about constant temperature. If you are changing with the temperature, again this changes. K is K naught into e power minus E by RT. Right now, as a first step, I am thinking only K is, that is, temperature is not changing. Am I right? Temperature is maintained at a constant. Okay. So let us see now. Yeah. Now let us again redraw all that. Now let us put this fellow here. This is getting disturbed me. So let us assume here. Now I am drawing again here. This is the solid, which is solid, and this is the gas, right? This is the gas film, right? So this is the gas film. Entire thing is gas film. Now, where is my particular thing? My fellow is somewhere here, outside, right? So let this fellow should penetrate through this. This is the gas, and this is the solid surface. Let the concentration of the gas at this bulk. This is the bulk phase. Bulk phase. At the bulk phase is CAG. Ca is the concentration of A. A, you are assuming it is gas. In the gas phase, CAG. G in the sense it is gas. Okay. Now let this particular concentration at this particular thing, since it is a solid, is there. Now at this particular point, let this concentration is CAS. That is concentration of A at the surface. The concentration of A at the gas film, the concentration of A at the surface will be different. That is why there is a diffusion. You understand? Because there is a change in concentration, therefore diffusion plays an important role. So if you want to write your rate for the first reaction, first step, that is the diffusion, the rate of mass transfer of A through the gas film by diffusion per unit surface to surface of B is minus RA1. This is the one is nothing but first step, double dash because you are writing for a unit surface area. Am I right? You can see in the previous class. Yeah, here double dash because you are writing for a unit surface area. If you are writing for a mass of a solid, you generally put one dash. This is the usual notation, right? So you are putting R double dash. One tells it is for first step. RA, A is the gas here, is nothing but minus 1 by S. S is nothing but the surface area, interfacial surface area at this particular point. Is minus 1 by S into dNA by dt, correct? This is the rate, how you write. This rate can be written in terms of, again, K. K is nothing but Kg, the mass transfer coefficient. Mass transfer coefficient in a gas phase is Kg. Let it be Kg. So Kg into is nothing but concentration term. Just like in the previous case, you are writing A gives R, you are writing minus RA is nothing but K into Ca, right? This is K. So K into Ca, K is nothing but the temperature dependent term, and Ca is nothing but the concentration dependent term. This is the concentration dependent term, and this is the temperature dependent term or rate dependent term. So K you are writing in terms of Kg because the mass transfer coefficient at the bulk phase is Kg, right? So Kg into what is the Ca? Ca is nothing but there is a diffusion. You are writing for a mass transfer. You take so therefore CAG, the concentration at the gas film, will be much higher than the concentration at the surface. Therefore, CAG minus CAS. Yeah, how many people not able to understand this? Yeah, please. Yeah, how many people not able to understand this step? Yeah, please read it out in this step. This is solid. This is the gas. The concentration is, this is CAS, and here the concentration is CAG. So you are going from here to here. There is a difference in the concentration. That is what this into Kg. Kg is nothing but here. The mass transfer coefficient in the gas film is Kg. Yeah. Hear it out, ma? This is solid. This is gas. Yeah. Yeah, I'm not able to get any feedback.
Sir?
Any doubt?
So the rate can rate is directly dependent on the mass transfer here. The rate is almost equal to the mass transfer in this case.
The rate is proportional to mass transfer into concentration dependent term. This is the mass
Oh.
transfer, and this
Oh,
is the
right.
kinetic term. We already discussed in the first class, right? That is
Yes, sir,
theory
yes, sir.
1.
Yeah,
Minus
yeah.
RA is K into CA. That is concentration dependent term is this, and the rate dependent term is this, right? So
So that
concentration
K,
term into
so what is that?
yeah,
Sorry, sir. What is that K again?
K is nothing but kinetics. K into CA. What is K? Rate constant.
Oh, the rate constant. Okay.
Yeah.
I thought it was the mass transfer coefficient. Okay.
Yeah, rate constant or mass transfer coefficient or whatever you name here. Okay. So Kg is the mass transfer coefficient or whatever it is there in the gas film. So there is a difference between this concentration and this concentration. Therefore, CAG minus CAS. So how much of the gas is being transported from this onto the solid surface, you can find out from this equation. So how much gas is going onto the solid, that much amount of the solid gas should react on the solid. Correct? That is what we equate. So second step. The rate of a reaction based on the unit surface area of B. Here on the surface, let it be RA double dash 2. This is for the second step. Is equal to minus 1 by S into dNA by dt. That is the disappearance of A with respect to the time. That is equal to, here there is a reaction here happening. How much is the reaction again? K dot, what do you call it? Double prime. Let it be the rate at this particular surface. The rate at this particular surface, let it be K prime, K double prime. So K double prime, this is the what do you call mass transfer rate, or whatever you call. This is the kinetic into the concentration. There is only one concentration because you are assuming that the solid is not being formed any ash. That is what your assumption here. No ash is formed. Therefore, what is happening? The solid surface is at a same what do you call concentration CAS. Therefore, it is CAS. You won't write the third step because this is the desorption. We want only how much gas is being penetrated through this particular gas film and going to the solid surface, and how much of the gas is going to the solid surface, that much of the gas is being reacted on the solid surface to give you the product. So out of the 3 steps, we write only the 2 steps here. First step is the gas penetration through the gas film. The second one is the reaction. Yeah, any doubt in the second thing? The second step. Here you are not writing minus like this because the solid is at the same concentration. The solid is not changing. If there is a gas film, if there is a ash film which is being formed, then there will be a concentration difference. Since you are assuming there is no ash film, you are writing CAS. If there is a ash film, that we will see when there is a catalyzed reactions, right? So here CAS minus something will come. But here we are assuming there is no ash film which is being formed. Therefore, K prime CAS. K prime is nothing but the rate at this particular here, right? And Kg is the rate at this particular thing. That you call it as mass transfer coefficients. This K generally we call it as coefficients, mass transfer coefficients. Okay. Now these 2 steps are in series because how much gas is being penetrated, that much of the gas is only reacted on the surface. The gas which is not penetrated through this particular gas film will not react here because the gas is not at all on the surface. How much gas is being on the surface, that much of the gas is only reacted. So you make that into picture. So at a steady state, the flux of A on the surface is equal to the reaction. That is how much of the gas is being going inside. So what is the flux? Flux is nothing but how much of the gas is being transported per unit area. Per unit area is nothing but flux. how much of gas is there at this particular surface, that much of the gas is being reacted on the surface. That is what the surface reaction. So if you equate this rate with this particular rate, because this is series and at a steady state, if you equate these two, what will happen now? This is equal to this, but the RHS or LHS, Kg into CAG minus CAS is equal to K prime CAS. Correct? Now that is what I will do. Kg CAG minus CAS is equal to K prime CAS. So take all the CAS terms to one side. So you split this particular thing, Kg CAG minus Kg CAS. If you are taking this side, it will become positive. Then you take out CAS common. Therefore, Kg CAG is equal to K prime plus Kg into CAS. But what we want this fellow. We want this fellow. We don't know what is the concentration of the gas on the surface. We know what is CAG. Because CAG will be given at the starting. What is the gas concentration? We know. But what is the concentration of the gas at the surface? We don't know. So unknown is CAS. So if you're writing this unknown CAS in terms of knowns, so CAS is equal to Kg CAG divided by K prime plus Kg. Now you know this is unknown, but we want to find out what is this particular rate. Then the rate will be equal to what is the rate of a reaction on the surface. So Ra2 prime is minus S 1 by S into dNA by dt is R prime into CAS. We don't know what is the CAS. This CAS, if you substitute this, then what will happen? Minus Ra prime is equal to minus Ra prime is equal to K. Instead of this K prime, you substitute, instead of this CAS, you substitute this. So K prime into Kg divided by K prime plus Kg into CAG. Yeah, how many of you understood this? Yeah. If there is a reaction, A is giving you R, or A plus B is giving you R, if this is a homogeneous reaction, then we write minus Ra is equal to K into Ca into Cb, right? But if there is a heterogeneous reaction, your K you cannot write like that. So here this is how you write. So minus Ra or whatever you prime you give is equal to K. This will be different into Ca or CAG because this is gas phase, that is Ca, right? So this K, what you write, you have to write as like this. How many phases are involved? You have to write like this. We still do some modification to this so that it will be easier for us to understand. Till here, any doubt? Then we'll go ahead because we'll write this in a simpler form now. I think you people are not responding to me. Yes.
Sir, I'm still confused. Can you go back to the first reaction rate you showed, sir? No, sir. In this slide.
Yes.
So that first equation.
Yeah.
Is that a mass transfer equation or is that a reaction rate equation, sir?
This is the mass transfer coefficient, right? So you are writing this is the rate. This rate, if you can find out this, it is fine. How much A is disappearing. This is unmeasurable. You are writing in terms of measurables. That measurable writing is nothing but concentration term into the rate term. So Kg is the rate into the concentration dependent term. What is the concentration dependent term here? It is not CAG alone because it is the penetration of this CAG onto the surface. The concentration of gas at this point and this point is different.
Okay. Okay.
Just like now
So the
you are
disappear
coming.
was okay, sir. So the first equation describes the disappearance of A by diffusion into the.
Yes, how much of the gas is being, that is what the rate of mass transfer of A through gas film by diffusion per unit
Okay.
surface to the B.
Okay. So what is the difference between the first and the second one, sir?
The
What is
second one is how much is diffused, that much is reacted. This is the reaction where it is happening. The reaction is happening on the surface. The reaction is not happening here.
Hmm. Hmm. Okay. So this
Just
K.
like I'll tell you one example. Now you are coming to college. That doesn't coming to college. That does not mean that you are in the class. You may be in canteen. You may be in a sports block. So this fellow is coming to the college. How much gas is there in the college? That fellow may not come into the chemical department. Let us assume this is the chemical department. College is big. You can be in a sports complex. You can be in a canteen or somewhere. But how much you are coming into the chemical department, that is what we will consider you as a attendance. Am I right? The same here. The gas is everywhere. How everywhere gas is not being present on the surface of the solid. On the surface of the solid, only some fraction of the gas is being present. How much fraction of the gas is being present, that much is getting reacted. That is what this. How much of the gas is being there here or concentration, how much is the concentration here, that tells you about this, the rate of diffusion. There should be a concentration gradient, then only the gas is being penetrated from the bulb to the solid. To make you still clear, can I give one more example? Yeah.
No, sir, I got that. I understood that concept, sir. So what is the difference between kg and k prime?
Good question. Yeah, kg is the mass transfer coefficient in the gas film because it is transporting, right? The gas is being transported. The gas is being transported because of the concentration gradient. How much of the gas is being transported? It depends on its mass transfer coefficient. That is what you will be studying in the mass transfer.
Okay, sir. So k prime is?
K prime is the, at this particular thing, how much is the reaction is happening. That is nothing but K. This is the kinetic part. This is the mass transfer part. Till now, you didn't get the mass transfer into picture. Since mass transfer here is coming into picture, you get kg. Earlier case, this is the thing. Homogeneous, only this will come. K prime or K. Because the reaction is happening on the surface.
Okay. Okay, sir. Yeah.
So the K prime is the rate constant, sir.
Yes. Yeah, you can assume it is rate
Okay,
constant. If there is no mass transfer involved, this K prime is equal to K in homogeneous reaction. Because you are writing rate as K, that is the concentration, temperature dependent term into concentration dependent term. Since there is a mass transfer, the gas, all the gas is not on the surface, only some amount of gas is on the surface. How much gas is being on the surface, it depends on what is its gradient from bulk to here. How to calculate the gradient? This is the gradient. And how much is being transported depends on its mass transfer coefficient. So generally Kg is the mass transfer coefficient. As you tell, K prime or whatever you call it is called as the rate, rate constant. Yeah, absolutely correct in your terms. To make my point much clearer, I'll give you one more example, right? So that this concept you should understand. Then only whatever I'm going to teach, everything is based on this. The entire 5 units is based on only these 2 steps. Yeah. One more example I'll give. You take a gulab jamun, right? You assume this solid is a gulab jamun, right? Gulab jamun is having a porous thing, right? That is fried gulab jamun. This gas, or what you call this, you assume it is a syrup. This is a liquid syrup. You assume fluid can be gas or liquid, whatever you want. So my example, what I'm giving, it is a liquid. This is the gulab jamun. The moment you are putting the fried gulab jamun into the mixture or syrup, sugar syrup, yeah, what is happening? The sugar syrup will go into the pores of this particular solid. Correct? Is it correct?
Yes, sir.
If there is no resistance in this particular phase, if there is no resistance in the water phase, let it be slurry. Let us put again here one more. Yeah. Let us assume our particular thing is here gulab jamun, and this is the liquid, right? This is the syrup, and this is the gulab jamun. G is the gulab jamun, right? So this will have pores, right? Now the liquid, the syrup, this is the bulk syrup, right? Bulk syrup is having one concentration. It should go through this particular pores, am I right? If there is no resistance here, then what will happen? The entire liquid will go inside. But if you cut this gulab, you take out this gulab jamun and then cut the gulab jamun. This is the half part of it. Your gulab jamun might be entering only to this, not to the core. Am I right? That is what you get uncooked, we call. Inside there will be a core, which is not at all boiled or whatever you call. If there is a boiled entire, this syrup will go through entire thing. So what I mean to tell is there is some resistance in this bulk phase. There will be some resistance in the bulk phase. The resistance, it offers some resistance. Therefore, the entire amount of the sugar syrup is not going inside. Only the sugar syrup will go inside only if it is present here. Once it is present here, it will go inside. But there will be some resistance here to go inside. Just like you are having one door, right? One door is there. If something happens inside some fire accident, everyone should go through one hole, right? One same door. So what will happen? There will be fighting among your friends. Who will go first? Correct? Did they not fight? Huh? Some boys will fight with boys and girls will fight with girls. Everyone wants to try to go out. In that process, what will happen? Some amount of extra time you will be spending at the entrance. Once you cross the entrance, you are free to move. The same thing will happen here. The gas, there will be some fighting for the gas to go into this particular solid. That is pores of the solid. Because the pores of the solid is limited, but the gas is unlimited. Only some amount of the gas will go here. Who will go and sit on the active side? That is what, there will be a big fighting among them. That is what we call as a gas resistance. Once it sits, then your product is formed. That is what you are giving here. Product is formed on the surface. There will be a resistance. When there is a phase change, there will be a resistance at the interface. That is what we call. When there is a gulab jamun in the syrup, there will be a resistance of the syrup to go into the gulab jamun at the interface. Once it goes into the gulab jamun, then it will goes to the inner core. That is what we are entire CR is all about. There will be some resistance when there is a phase change, especially at the interface. Yeah. Did I make my point clear? Still not clear? Yeah, some of you can give the feedback.
It's clear, sir.
Yeah, can we go for the next one now? Now this is how we are getting. We'll do this some gimmick here to make it much simpler, right? That is what we are equating both the reactions. Then we are getting CAS. This is the unknown. Unknown you are writing in terms of knowns because mass transfer coefficient in gas phase, you know, concentration of a gas phase, you know, the rate of a reaction, you know. Therefore, The mass transfer coefficient at a gas phase also you know. Can we redo this? What you do is you make this reaction like this. So now this is minus Ra2 prime is equal to CAG divided by, you get this fellow down. Therefore, what will happen? K prime plus Kg divided by K prime Kg. Can I write like this? Can I write like, just I'm doing reverse of it. Now again, if I write minus Ra2 prime is equal to CAG divided by this fellow divided by this fellow divided by this fellow. So K prime divided by K prime CAG plus Kg divided by K prime CAG, correct? Sorry, Kg. Not CAG, this is Kg, right? Kg only, no? So K prime cancels, Kg cancels. So what you are left with is like this. Minus 1 by, yeah, you can see here, CAG divided by, this is get cancelled, minus 1 by Kg plus 1 by K prime, right? So that is what you are writing, 1 by Kg plus 1 by K prime CAG. What I'm doing, I can do this entire thing like this. Now this is nothing but an individual mass transfer coefficient. Kg is the gas, K prime is the what do you call mass transfer coefficient at the solid surface. Therefore, 1 by is nothing but the individual mass transfer coefficient. This entire thing is nothing but the overall mass transfer coefficient. So this expression is for the overall rate in terms of bulk reactant concentrations. Can I write like this? So individual, your overall is nothing but the sum of the individual mass transfer or coefficient. That is what you will study in the second. That is CRE2 mass transfer 1, say unit number 2. The what do you call the what is that number? The relationship between the overall mass transfer coefficient and individual mass transfer coefficient. This is the overall. So this is the individual, each one. Am I right? Yeah, I'll stop here because still a lot of discussion will go on here. I don't think I can complete the discussion now because still some more things are there. I need to explain a bit more. So till here, any doubt? This equation, you are getting minus Ra is nothing but 1 by this particular thing into CAG. This 1 by this particular thing is nothing but K overall. Correct? Yeah, earlier you are writing K into CAG in a homogeneous. K is the overall. But here K you cannot write like that because it is a sum of individual mass transfer coefficients. Therefore, you will write like this. Yeah, I think I'll stop here. If any doubt, yeah, some questions I can take. Yeah, ma? Any doubt? If no doubts, I'll stop recording.
Hello.
Yeah, go ahead, ma.